Okay, so we try not to be late, so let's start now. So our next presentation is from NXP, so about fault-tolerant Internet communication in future car architectures. So the speaker will be Stefan Lorenz, so from NXP. He's a senior principal system architect. Since 2010, he's acting in various roles for automotive Internet at NXP. He is responsible for definition of Internet products and represents NXP in various Open Alliance technical committees. So I'll say no more. Well, the stage is yours now. So yeah.
Thank you. Yeah, welcome to my presentation, and thank you for showing in. I hope the coffee was good enough that you still have some energy to listening in. And I want to share this picture with you, and I found it quite nice when I saw it on a hiking trail somewhere in the US. Traveling at your own risk beyond this point. And this is a bit what was in the past in the car. So when the sensors detected, oh, it's not working, it was switched off. And to the driver, it showed a light to say, okay, your ACC or whatever is now switched off. So travel on your own risk. If we go for autonomous driving cars or getting more autonomous functions into the car, that doesn't work anymore, right? So we cannot say we're switching off because it's the aim of the car to drive. So this one doesn't work anymore. And Brian earlier also nicely said there's much more to function the safety than what he showed in making the network right. And I will cover a bit another part of what needs to be done to make the network safe. So yeah, first of all, give a bit of the context of the system and what I'm talking about, and then looking into cascading faults, which is one of the phenomena or the issues that needs to be covered to make sure that at the end the system stays safe. And then also talk about a bit fault containment region to say how can we cope with this, and then get to a conclusion. So starting with the system context, we all see that those networks are going into zonal and software defined. And there are different ways, so distributed compute, central compute, or HP zonal compute. But in principle, what they have common, they distribute the safety functions over the network, which was in the past somewhere in one local ECU, is now distributed over the network, and the network becomes part of it. We also have aggregated and mixed critical data over the network. So it's shared different data, and it's used for level 3 and above autonomous driving. So with this, there are coming some more requirements. I said this in the beginning. The fail-safe operation is not sufficient anymore. So we cannot switch off the thing. We need to make sure that it keeps operating. So what we need in case of fault, we need to keep operating. The system needs to stay running until the driver is able to take over, if you are in the lower levels above 3, or if it is a full safe-driving car, then the car needs to stop in a controlled way if it is not able to secure further. So for this, the system itself needs to be fail operational, and we also saw this nicely from Brian earlier in this talk. And at least for the time which is needed to make the so-called minimum risk maneuver. So this is actually the case where the car securely stopped. But also for this, we need to have the system running, right? It's a part of the system which needs to do this. It might be degraded, so just stopping the car, but it needs to be still safe. If we look to the network itself, it needs the network to be fault tolerant. So there must be a certain part of the network still available. And even if they are fault, we cannot just switch it off. And if we talk about the network availability, and you already see it's more than the safety, or it's actually specific points. It is the availability of the network. And we need to make sure that the critical part which we need, we cannot lose. So how to do this? And to make this, I need to make a step back and see what faults do we have. We have systematic faults, so which are manifested in a certain way. So whenever you are in a certain situation, you always get this fault. And we have random hardware faults. So you don't know where it happens, but it might happen somewhere. And they are probabilistically distributed, but they are unpredictable. So you don't know when they will happen, and you can also not say it will happen in the same situation again. Today, this part will more be on the random hardware fault. On the systematic faults, I already talked earlier this year in the Automotive Ethernet Congress. So when we talk about faults, so what is this? The ISO 26262 says to this, it's an abnormal condition that can cause an element or an item to fail. So quite easy. And it further splits it up in different faults that can happen. So it can have the permanent or intermittent faults, which just stay until they remove. So if it is a permanent fault, of course, you need to repair it by replacing something. And they are transient faults. So this is something typically soft errors, so where a bit is flipped, and then if you write it correctly again, then it's repaired. So they might disappear autonomously, or at least you can repair them in the system. And if we look to them for the permanent faults, we need to mitigate them, so we need to deal with this. And for the transient faults, we should try to get them solved. Right, so recover from there to continue operation, because we don't want to stay in there. And if you now look to our system, and also, so you see there's a lot of repetition from Brian this morning, or earlier today. So especially on those systems like the brake, the steering, you have the high ASIL requirements. And for those systems, you need to make sure that the functions, or that you have functional redundancy in the network. And there are other network or other parts, so like the front wiping, so you can degrade it if it's not working. But it depends a bit on how they are distributed over the network, right? So you might have certain parts which are still relevant for braking, even though there's also other functions on it. And now there are three ways to prevent those dependent failures in this, in the redundancy, because you need to make sure that your redundancy is safe. And one fault which typically can happen is fault of shared resources. So if you have a random network, but it runs from a battery, then of course if the battery fails, there's the shared resources, and then you would lose both of your redundancies. The second part is systematic faults. So if you have something in which systematically on a certain point fails. And the third part, and this is where I will get deeper into this, is so-called cascading failures or cascading faults. So that means if a certain function is failing based on another failure. And I will get deeper into this, what it actually is. And I made a very simplified network diagram, but you also find back the wing there. So you have some ECUs, they are connected, and they might have redundancy over CB or VLAN redundancy, and so it's a hardware redundancy in the network. We also see that it should be a static redundancy. So sometimes there are ideas of doing something to switching off or rechange the network in case of a fault, but the timing requirement typically doesn't allow it, right? So we need to have something which is permanently active. So what happens if we have now a fault there in one of the network? Of course, we have the second part, and how this can work we saw earlier today. But in this case, you have the redundancy, and there's a failure in one network. And if there is a failure in the second network, So that's, if it is the same kind of failure, it's a square of the probability. If it is a different failure, it's just the one probability of the failure multiplied by the second one, which is very unlikely that those are happening at a certain time, at the same time in your network. So you still have the chance to stop the car at least securely if part of your network fails, because you have the second fault. But what happens if one fault is causing that the other fault is happening? Then you get a probability which is just the probability of the first fault. Because you have this cascading fault, and so one is leading to the other failing. And if this happens in both of your networks, then you're losing your redundancy. And some simple examples. So if you have, assuming the switch, you have two ports and you have a shared supply. And if you get a short circuit on one of those files, for example, there, and this one is a hard short which is making your supply to drop, then you will also have a failure in the second device. In the second port. So if you use those two ports for the redundancy, then you might lose both at the same time because of the fault in one of those networks. The second example is the TCAM. So you might have in your TCAM a forwarding rule that certain messages get forwarded to a certain port. But if you have a fault in there that makes the messages sent to a different port, then you might have traffic congestion on that port. So you might kill some messages which were normally run through. So you overload the remaining network, and this can also lead to loss of the redundancy. And the third example is if you have a soft error somewhere in the network, and let's assume it's somewhere in the one port, and you want to solve it. So I said soft errors should be corrected, and so you might need to reconfigure it or to reset it. And so what happens if you reset it, and you need to reset probably the whole thing, then you also lose your switch and you lose your second port. And typically, resetting the communication takes longer than 200 milliseconds. If you completely need to restart, you saw earlier on the MACsec resynchronization, so you need to reestablish your MACsec keys, etc. And why this is important, I will come on the next slide. So if we have now a fault in one of the networks, and we lose the redundancy, for the safety critical application, then we need to take the remaining part to make this minimum risk maneuver. And if we rely on the end-to-end mechanism, of course, we can detect it, but we don't know where it happens, right? So we cannot do much against it, but we can deal with this. So one might say, okay, in today's network, we even have a second channel by a CAN network next to this, just as a fallback. But even in this case, we don't want to have a cascading fault, because if we lose our redundancy in the main channel, then we would immediately need to make also there this minimum risk maneuver, because the CAN channel would then be the only thing which stays. So therefore, in case of this cascaded fault, we need to make sure we need to make sure to prevent the cascading faults, so that we don't run in this non-availability situation. And typically in the car network, we have those around 200 millisecond time, which is then used to start to the minimum risk maneuver. So what can we do? And I also said this in the beginning, we can do some fault containment regions. So that's one means to overcome this. And just generally, a fault containment region is a a method to prevent a failure from one channel or from one part of the network to impact the functionality of another channel, right? So we just try to separate it. And we want to limit the cascading effect of a failure to a low number of effects or low number of functions, so that most of the functions remains and we can rely on those remaining functions. And just a general example of this, so you see it quite often in microcontrollers, that you have several subsystems which are encapsulated and they have their own memory, their own peripherals. And if you have a failure in one of those cores, it will be limited to really this portion of it, and the remaining part can continue. Another example is an energy distribution, that you have a dedicated switch for certain parts to make sure that if you have a short circuit in one of the parts, you do not kill the complete network by shorting the power. So if we look now to our examples back, so what can we do? And one example would be, for this first case of the short circuit, to have a separated supply, right? So you can have different supply for the different ports to make sure that when you have a short circuit in there, that not only this supply, and of course it's not a different battery, right? So it might be a different rail of your controller, or even just separated routers to make sure that it's not getting an overload of one of the network. Another option would be to make sure that you have a current limitation of your sub-blocks, so that whenever there is a short circuit, you are not overloading the power supply. And then probably also the possibility to switch off this part, because another failure might be, if you have a short circuit in there, that you're overheating the device and then you need to shut off because of an over temperature. For the TCAM, the main thing to detect this is to overcome this is to detect the fault. Right? If you find the wrong configuration, you can reconfigure it and correct it. But you see here, I gave an example on this FHTI. So the time you need to handle the fault is around 10 milliseconds to prevent the cascading effects of those faults. And of course, you might have other means to prevent pointers to another port in case of a fault, which depends a bit on which kind of faults you cover and what you see, what might happen. And for the soft error, so you might want to detect the fault where it is, and then really only fix it on the portion where it is. So yeah, really just around the fault to have a small area which you can reset, which you can reconfigure without affecting the whole switch or the whole port. And typically, especially if it is in the port, you want to prevent the loss of the link, because then you would have the link startup time and the things around, so like re-establishing the MKA. But for sure, you want to have the other ports unaffected to make sure that you keep your redundancy in this network running. So if you look at this now on an overview, so in principle you can say, first of all, you need to detect and locate a failure. So it's not about being safe, but it's about being able to handle the fault and make sure that you keep the availability of your network. Secondly, and that's a bit the split up between the soft errors and the permanent errors, you want to repair it, but you want to repair it locally. So the better you can locally recover or reset a certain part, the less side effects you have on doing it. And for permanent errors, you need to have a safe state, at least on the port level or certain function level, so that you make sure you switch off this function to make sure it's not affecting the system, and then notify the system so that on higher level system actions can be taken. If you now look what this means for an Ethernet switch device, what it needs to do. So first of all, it needs to have the detection capability, but those detection capabilities also need to have a latent fault, because you need to make sure that your detection of the fault really works. And so therefore you need to have detection fault methods. Then on the soft errors, ideally you have error correction where possible, so like ECC for memories. But you also need to have the independent possibility of certain sub-functions, sub-blocks to be reset or reconfigured individually. And then on permanent errors, to have those safe states, so have local safe states for the different parts and not one global safe state of the device. And for this to have the whole system safety concept to say which parts I can switch off and which part is affected, because also you need to consider then in your redundancy probably which parts can be used for redundancy and which one have a dependency in the network or in the device. So, and this brings me to the conclusion. And what did I show? First of all, we need to have fault-tolerant communication networks to serve the fail operational system needs. And for this, fault containment regions is one of the means to prevent cascading faults, to make sure we get the network fail operational. And if we look to switches, they need to be able to detect the faults and have this local recovery or degradation possibilities. And finally, or summarizing of this, to make the keep the availability high from the communication side, we want to prevent that the end-to-end protection needs to kick in to start any action on the car system to securely stop the car. And I always say we do not make the car safer with the network, but with making the network available, we also need to make, or we also will make the car function available. And maybe to sum it up, and there was it also mentioned in the SUX presentation this morning, with autonomous driving cars, we're also getting more into driving as a service. And with this, we also need to make sure that the service stays available. And we don't want to make the cars stopping somewhere when we are transporting passengers. And with this, I'm at the end. And thank you for your attention. And I'm open for questions.
Okay, so thank you, Stefan. So do we have any questions in the room? Yes.
Thank you for that outlining of fault handling. We had this morning that presentations on automotive software-defined networking. So in an overall context, of course, an SDN-capable vehicle provides the ability to do fault management. So in that case, on switch level, if the fault could not be resolved locally, then it might be that the manager has to be notified. So this is then the ability of fault management and alarm reporting, which has to be supported in context of an automotive SDN as well. And this would be then done by Young and state variables.
Yeah, correct. So that's quite important that detecting the failure is one thing, but it's quite important then to inform the network, and you might want to reconfigure it, right? To do some further operation or further actions then on the network reconfiguration. But for this short-term action to really decide if you can operate or if you need to stop the car, for example, there you wouldn't start reconfiguration. So you saw those kind of 200 milliseconds, and I doubt that you would reconfigure the network make it in a different way to make sure that you can continue driving. That might be something. If the car is stopped and you find, oh, there's something wrong, I can reconfigure to securely go to the garage to get it fixed, for example.
Yes, of course, there are many use case categories in fault management, and the very simplest one would be the fault could be resolved, but it has to be logged, in such a management data model.
Yeah, correct. I agree.
Okay, so next question. I think
thanks so much for the talk. 2 years ago, I sat in a conference on the wiring harness, and there was 2 people from BW giving a talk on power supply redundancy. How do we generate redundancy in the 12 and 48 volt board net? And arrogant as I am, I asked them, can we apply the methodology you applied to a communication network? And he basically told me, shut up and sit down. As long as we don't supply you power, your computer and your network does nothing. So looking at Thomas's talk from yesterday morning, do we need to bring the power supply people and the communications people closer together to solve this problem together? Or is it 2 problems that are solved separately and we can happily go our ways and hopefully we solve them at roughly the same time?
No, I think they need to be solved in common. And it really depends on the actual network, what is the right strategy to handle it. But a simple example, we also see a lot of discussions about RCPs, for example, so where you have less function in the nodes, but you get it in the central node. But if you lose the communication, you need to do something locally in the RCP as a safety action. But if you lose the communication, you need to make sure that you're not losing the power at the same time, because how should this device act if it loses the power, but also the communication? So I think this needs to be covered in common to make sure that at the end, the systems which needs to be available to make certain things in the car, that they are covered properly from power side, but also from the data side.
Thanks.
Okay.
I just wanted to bring some good news for you in terms of Ethernet bridging. For fault detection, we have a standard called Connectivity Fault Management, which is suitable for fault localization, as well as some detecting misconfigurations. So you may take a look at as a starting point. Some profiling might be needed to simplify for automotive, but there is a good basis already.
Yeah, thank you.
Okay.
So, Christoph Gollop, BMW. Thank you for outlining the different behaviors and the different faults, and I think it was pretty well explained. I just wanted to answer to the presentation and at least to the comment of Max. We have the problem in the car as a whole system. If communication goes away, we have a problem. If we lose power, we have a problem. But we have a lot of redundancies if you're speaking about self-driving cars. If you lose your braking system, also if you lose a relevant ECU and the whole network stays there, you also have a problem.
Yeah.
You have to solve all of them, or you stay at a level 2 and the driver is the redundancy. You can call it that way. What we never forget is that it's the whole system. Otherwise, we just make the availability of one part of it better. We don't get to a safe level of all.
Yeah. Thank you. I fully agree to this. So I think it's a good statement. Yeah, thank you.
So creating better availability is a good thing in itself.
Yes. Okay.
Okay, so I think we are just in time for the next presentation. So yeah, if we have no more questions, we can move to the next topic.